All right. Hello, everybody. Thank you for the opportunity to be here and speak to you about some of the work that we've been doing in this space. I feel woefully underdressed, but here we are on the road of life. Okay, so I'd like to tell you a little bit about quantum at Mason. And so what I think is best to start off with is, what quantum means. So this is a slide. That's who I am. I'm an associate professor of physics here at the university. I'm the director of our transdisciplinary Center for Advanced Study in Quantum Science and Engineering. Okay, so you may have been hearing quantum colloquially bandied about in the news here and there. And so what I want to talk about first is what that actually means. And it won't be a physics lecture, don't worry. But what I want to just start out with is you accepting the fact that everybody in this room, everything in this room, is composed of many, many, many atoms. So all of your experiences on a day-to-day basis consist of you interacting with large atomic systems that are bonded together, interacting with each other, that are warm and messy and squishy, right? A single atom, therefore, may not be too surprising that just one might behave very differently from you yourself, right? So the properties of single atoms and single electrons, protons and neutrons, are radically different. They can exhibit very non-intuitive things. They can be in two states at the same time. Schrodinger's cat is a thought experiment example of that, where the cat is both alive and dead at the same time. Personally, I'm not a big fan of cats, so I don't have a huge problem with this. But I like dogs, so don't make a Schrodinger's dog. And they can also be in two places at the same time. And these effects may seem odd and non-intuitive, but they're actually better verified than the theory of gravity. So we know them better than we know gravitation. And the only reason you don't know about them is because you're big and you have lots of atoms. Now, my prior slide said the second quantum revolution. The first quantum revolution was about our ability to control the properties of matter. And so you're all using it right now. The silicon chip, right? Being able to grow silicon, dope silicon, and form it into giant circuits where you have 7 billion transistors interacting with each other. That was the first quantum revolution. But it didn't take advantage of the real quantumness, these non-intuitive, weird properties of matter. That's where we are right now. So where we're going right now as a species is being able to harness the actual non-intuitive aspects of particles, their quantumness, for technology. And what that can do for us is really game-changing. So one of the first areas, and probably areas you hear the most about, is in quantum computing. And this is about building new kinds of computers that utilize not the traditional bits, like zeros and ones that you have in the computer sitting on your desktop, but instead they utilize quantum bits. What does that mean? That means that the bit in the computer is a system which can do weird things, like it can be in two states at the same time. It can also be interacted with other bits such that all their states are mutually independent upon each other, or mutually dependent upon each other. In that case, the way you process information is really different, and it takes problems that are right now totally unsolvable for us and makes them solvable. Right, so we're anticipating huge advances in drug discovery, being able to model the interaction of molecules with each other, so being able to fully simulate molecular docking as one of the areas where this can have a big impact. Scheduling and optimization. We all like getting our Amazon packages, right? We like getting them on schedule at the times we expect. Scheduling problems actually can't be solved. The traveling salesman can't be solved with conventional computers. Only with quantum computers can you fully solve that problem. Other areas such as fluid dynamics and aeronautics, we anticipate big advances in there. Boeing is one of the first funders of this work. And then physics and chemistry, and of course, finance. A good friend of mine was just poached from Johns Hopkins APL by JP Morgan. So he's a vice president over there. He's very happy, right? So big advancements in solving problems are coming with quantum computing. Also, quantum sensing. You don't hear as much about this, but this is already real. Have you guys heard about the discovery of gravitational waves before? So if you don't know what those are, it's really, really cool. So when you move through space is really like a fabric that you exist on. And if you think about the planets in the solar system, right? Planets are going around and around and around and around. And why are they doing that? You can think about it as you have a big rubber sheet and you put a bowling ball in the middle, right? And that makes the sheet bend. Right? That's what gravity is. It's a curvature of the fabric of space-time itself that you get to exist on. And so the reason that your planets go around and around the sun is because they're following the curvature of that fabric. Now imagine if you had a bowling ball, and you started to shake it. You start move it around and wiggle it here and there. What would it do? It will send ripples out through that rubber, right? And those ripples would come out and propagate away. Those are gravitational waves. Gravitational waves sound pretty cool, right? But it's actually even more cool than that. It's actually stretching and compressing the fabric of reality itself. So what that would correspond to you is your whole body getting compressed and stretched out again and compressed and stretched out again. And so we can now detect these, even though they're millions of light years away. We are detecting two black holes that are wobbling around each other and actually stretching and compressing space-time itself, right? And the only way we're able to do that is by preparing quantum states and using their sensitivity to the environment to detect these alterations in space-time. So it's a huge, huge coup for both science, we discovered these things, but also in our ability to probe the universe. And so detecting the I don't know why I'm trying to use the laser. Detecting the undetectable is really what quantum sensing is all about. And it's not just there. It's also in position, navigation, and timing for our armed forces. GPS is really easy to spoof, and it's really easy to deny. Our soldiers need to know where they are, and they need to know what time it is, but also in other areas of biological health, finding new ways to probe human health and biological systems. Okay, I'm running over because I always do. But that's what you do when you're a professor, right? Nobody can turn off your mic. I guess you can, though. So quantum communication, though, is another area where this is poised to have a really big impact. And I've titled this Ultimate Security and Insecurity. Why that? Because quantum computers can break RSA encryption, as we know it right now. So this is why the NSA is very interested in this. Public key encryption goes bye-bye once somebody has a quantum computer. We would like to have one, for obvious reasons, but might not be so good if our adversaries have one. So not only are we working on building quantum computers, we're also trying to find ways to create perfectly secure encryption keys and distribute them, right? So that we can have perfect confidence that our systems are secure. And the last area I think is the most important, and it's an area where Mason is really leading the country, and in my opinion, the world. There's a worldwide shortage of people, of quantum literate scientists and engineers who are actually able to do this work. This is a major problem, and it's a problem that we can only solve by fully engaging our population. The US's future economic and national security is critically dependent upon building up a workforce that can actually advance in this space, right? And so in this case, diversity, equity, inclusion are an actual requirement for the future security of this country, not some sort of thing you just tack on, right? Like sometimes people do. Okay, so let me just give you an overview of the global efforts in this, and you can see where the US stands compared to other countries. And this chart's a little bit, higgledy-piggledy, but since 2018, the US has been putting in about $1.2 billion. This chart is circa 2021. China, by that time, had put in $10 billion. So we are being outspent by nearly a factor of 5, and money is progress in this field. Since then, I updated it with this other bar chart, which is a bit easier to read. The expenditures by other countries have advanced even further. China's at 15 billion, the US is almost at 2, and the European nearly triples our expenditures. It spends $7.2 billion in this area. So we are not the only ones interested, and if you use dollars as a measure of progress, we are way behind, right? So we need to do more. So QSEC, the Quantum Science Engineering Center, was created in response to this. We're a transdisciplinary center founded in 2018. We have 7 member departments. Our departments are diverse: physics, math, computer science, chemistry, ECE, mechanical engineering, and education. We want to impact in all these areas. It shows you how diverse a field this is. We have active efforts in quantum computing and algorithms, quantum sensing, and quantum materials, and we are dedicated to building a world-class quantum workforce with equity at its core. And key in that effort is close consultation with industry. We don't want to be designing degree programs and certifications that academics think are good and interesting. We want to be talking to industry and figuring out, there's a workforce shortage, what do you need, and how can we get that to you quickly? So I really loved he's gone. He was here earlier, though. The business school was talking about, we're in the success-making business. That's what we want to do. And our students at George Mason are not traditional students. They're non-traditional. And what we're talking about here is potentially bootstrapping a lot of people who might be first-generation college students, right? Or into like one of the most advanced and exciting and fast-moving industries of our time. I mean, this is like a once-in-a-generation technological revolution. So there's a chance for a massive impact here. And we work with companies. I don't have enough time. Oh, the one thing I'll highlight, the QEDC, the Quantum Economic Development Consortium, was mandated by the federal government's National Quantum Initiative. Mason was one of 7 founding universities for that organization. So we, again, continue to be altogether different and have an outsized impact for ourselves. Okay? In terms of QSEC, we've been cost positive for the university. Our indirects exceed our seed funding from the university in each year, and our research expenditures, which is the dark green bar, continue to grow. I'll very quickly highlight a few things we're doing, and then I'll turn it over to one of our quantum success stories, my former student and now professional quantum, I don't know, what do they call you? Quantum physicist. I didn't know if they threw an engineer in there or not. And then I'll turn it over to him he'll tell you about his path. So quantum at Mason, what do? We have people working on algorithms for optimization. When you have a computer that processes information in a new way, you need to talk to it in a new way. Traditional C++ and Python don't work. So we need to find a way to cast our problems in a way that these computers can do something with it. Next, we have quantum sensing. Would you believe that Mason has the world record for the most sensitive quantum magnetometer and gradiometer on the planet? And that individual who's done this, Dr. Karen Sauer in the physics department, has been competing with far more funded groups to achieve that record year after year. So it's bandied about back and forth. Karen started with a lab with a bunch of random equipment in it and no startup funding when she came here. So for her to accomplish this is remarkable. Quantum materials, I talked to you about atoms and electrons, but it might be better if I could hand you a crystal and say, here, this does something quantum-y. We're working on growing materials and probing materials to find ones that do quantum-y things. And we're doing that here on the Fairfax campus. We grow the materials and we measure them at temperatures that are colder than space itself, right? And at very high magnetic fields to probe their properties. Right? And finally, quantum workforce and education. We're grateful to Congresswoman Wexton for helping us secure a $650,000 community partnership grant. We're using that to train elementary school, K-12 and up, and K-12 teachers in how to incorporate quantum in their classrooms, how to instill a fascination and love of this beautiful science and engineering area early in their students. And we're also, we're paying them for that, by the way, which is really important. Teacher time is valuable and they deserve to be compensated. And we are also having an immersion program for high school students. We're trying to identify students who are not part of the typical science and engineering pipeline and give them paid internships, $15 an hour paid internships, so that they don't have to choose between working to support their families and getting key experiences that can help them make that next step into a university education. And we're very passionate about the workforce and education part. I think we love our research, but I think it's very inspiring and exciting to know the impact we can have on human lives here. So that's great. And